Thank you, Emma, and thanks for the invitation and thanks for turning up. So the name Schrödinger goes with cats. We just know that. So I have three. So this is Fat Jack, the one-eyed cat, and this is Jessie, and it was named after Jessie Breaking Bad, and this little kitten. Okay, so we may get two cats. We'll see how we go. Right, Schrödinger wave equation, folks. Here we go. Why am I talking about this? Because it's 100 years since Schrödinger came up with his wave equation in 1926. So let's start with a little bit of history, because that's always a very good place to start. And Daniel mentioned Newton, as he wouldn't be a very good scientist today. He was a good looking bloke though, wasn't he? Here, anyway. 1686, three laws of motion, okay, those ones that you learned in high school physics. And as a result of those laws of motion, basically determinism. That meant that the universe is predetermined, okay? Everything's predestined. You can calculate the exact form of the universe at any time in the future, okay? Which, when you think about it, it's pretty cool. You know what's going to happen. And that sort of held sway for a couple of hundred years, and then at the end of the 18th century, the physicists, bless them, honestly, they thought that they had everything figured out except one thing. And they reckon when they sorted out this one thing, there'd be no more physics. They wouldn't need physics anymore. Everything they needed to know, they could know. And that little thing was atomic spectra. And funnily enough, they couldn't do that. Along came this guy here, Max Planck, and he was the first sort of quantum scientist. He was studying black body radiation, so the emission of color from bodies that you heat up and they emit color. He was trying to get a mathematical description of that. He did, but in order to do that, he had to invoke this thing called quantization, and the fact that energy was not discrete, it came in packets, okay? It couldn't have any value that it wanted. E equals h nu was his famous equation. Einstein came along 5 or so years later, and he sort of backed this up with his study of heat capacities of solids. In other words, how solids heat up, how much temperature rise you get from putting a certain amount of heat into a solid. He confirmed quantization through that study. He also did the photoelectric effect, where you'd shoot photons at a metal surface. They would bump off electrons, but only when your photons had a particular energy, and above that it had nothing to do with intensity, it was all to do with energy. And so that was sort of the important background of what we're going to be talking about. Then came Niels Bohr in 1913, and he came up with the structure of the hydrogen atom. He was trying to remember this at the very, very early days. Rutherford came up with the idea of the atom being a positively charged nucleus, the electrons somewhere around it. And then Bohr came up with a mathematical model that described the hydrogen atom absolutely perfectly. And here was the emission spectrum of the hydrogen atom. That was what he was trying to get a mathematical model of. And he did that, and this was his model. He said, right, we've got your nucleus here, it's got a positive charge. Here's your electrons, and these electrons live in certain energy levels. They can't live between those energy levels. Those energies are quantized. They can't be any particular ones. And he said, right, the electron is orbiting the nucleus, blah, 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 blah. The maths worked brilliantly, but the basic physics didn't, because if you have a moving electric charge like that, it loses energy and it'll spiral into the nucleus quicker than you know. So, the maths made sense, but the physics didn't, and so we needed a new physics at that stage. And so, 1925, wave mechanics was born, and this was in fact the first quantum mechanics. This predated the Schrödinger wave equation, and this was invented by three people. The first of them, Werner Heisenberg, who you all know. Waiting for the recognition there. No, okay. This is actually Heisenberg, of course it is, okay. And he, in 1925, had an epiphany. In June 1925, he went to a little island off the coast of Germany called Heligoland. And there he came up with matrix mechanics. God knows how. There's YouTube videos on all of this stuff, but he came up with this new physics that was absolutely required. And he was very excited about this, so he went and reported this to two of his colleagues, Max Born, who was this very stern-looking fellow here. Right, who's that? See, the Australian in the room, got it in one, Strine, okay. That's Olivia Newton-John. Why is she in a quantum mechanics talk?
She's his granddaughter.
Oh, damn it, you. Okay, right. Yes, very good, very good. Olivia Newton-John is Max Born's granddaughter. There you go. And this guy here, Pascal Jordan, nothing interesting about him. He apparently had to be denazified at the end of World War II. But, so these guys came up with matrix mechanics, and this is a very sort of arcane, obscure mathematical sort of formulation of quantum mechanics. And then Heisenberg came along the year after and developed wave mechanics, which is another formulation of quantum mechanics, okay? So, it was just known in 1924, French guy Louis de Broglie, 1924, found out that electrons had wave properties, that matter had wave properties. And here it is. Here it is. This is the Schrödinger wave equation, okay? H hat psi equals E psi, okay? And you're all thinking, shit, why can't we just cancel out the si's and we get H hat equals E? I mean, that's obvious, isn't it? Okay, except it's a special equation. It's an eigenvalue equation. So this thing here, this H hat is an operator. It's a mathematical operator which operates on this thing here, which is a wave function. We'll see why it's called a wave function. And this thing here is your energy multiplied by your wave function. So again, some of you might have learned about eigenfunctions, eigenvalues, maybe in sort of first year uni maths classes, stuff like that. So this was a probably simpler application of quantum mechanics that Schrödinger came up with, the wave mechanical formulation of quantum mechanics. Okay, so we're going to solve the Schrödinger wave equation. Yeehaw, okay? Has anybody actually done this in like physics or maths or chemistry? No? Great, okay, here we go. Particle in a one-dimensional box. Nobody's ever done that? Brilliant, right. One-dimensional box, okay? So we've got a one-dimensional box. The sides of the box are infinitely high, so the particle can't get out of the box. It is constrained to move between x equals 0 and x equals L. It's the only place in the world that that particle can go, okay? Simplest possible application of the Schrödinger wave equation. So, how do we treat this? Well, funnily enough, we start with classical mechanics. And classical mechanics gives us a thing called the Hamiltonian operator, okay?
Alan, I've
Yeah.
got a question.
Yeah.
The box has got two sides. Why isn't it 2D?
No. It can only go there to there. There
So
to
where
there.
do the sides come in?
The side, so it can't go out here.
Oh, I'm sorry.
Here we go, right, okay. That's good question. Good. Right, so classical mechanics, we get this thing called the Hamiltonian operator, and we can take the classical Hamiltonian operator, we can convert it to the quantum mechanical Hamiltonian operator using these postulates of quantum mechanics that Schrödinger came up with, okay? We're not going to go into them, you'll be happy to know, but this is what the Hamiltonian operator looks like, and you're thinking already, oh my God, why did I come to this? What do we got? We've got complex numbers, we've got second partial derivatives. Oh, fantastic. Anyway, here is your Hamiltonian operator for the Schrödinger wave equation. There is your Schrödinger wave equation, H psi equals E psi. So we substitute this into this, and here you go. For the particle in the one-dimensional box, you've got to solve that equation. And already you're just going to sleep. You think, no, this is maths, I can't do this. Yes, you can, because you've all done calculus. Everyone in the room has done calculus. You have. So all that this equation is saying here is that you want a function, right, forget this, that's just a constant. We can forget that. Differentiate, forget the constant. You want a function whose second derivative is itself. Anybody know of such a function? When you take the second derivative of a particular function, you get it back? Exponential, absolutely. Exponential, damn it, why did you say that? Yes, it's good, but it doesn't work for reasons that we're not going to go into. Any others? Okay, no others. Sine. Sine x. Okay? A sine AX. You differentiate sine twice. Sine goes to cosine, cosine goes to negative sine. Okay? It comes back to itself. So there's a function that when you differentiate it twice comes back to itself. That's all good. So this is a potential solution for our equation here, some sort of sine function. Right, now quantum mechanics says that this function has to be well-behaved, quote unquote. It's got to be a well-behaved function. It's got to be finite, it's got to be single valued, and it's got to be continuous. And it's this continuous thing that's the interesting thing, okay? So this function has to be continuous both inside the box and outside the box. So the function has to be 0 outside the box because we know that the particle can't get outside the box. It can be any value it wants inside, but it's got to be 0 at that point there where the box meets the outside, and at that point there where the box meets the outside. And this is where quantization comes in, as we will see, okay? So when we make that proviso, we end up with a wave function that looks like that. It's just a glorified sine x, okay? And you get energies that correspond to the wave functions. And you also get these things called quantum numbers as well, which are really, really important, but we won't go there. Basically, you get these wave functions and their associated energies, and those are the equations for them, okay? Now, the interesting bit is what they look like. So, here are the first 3 wave functions for the particle in the box. And you can see they just do look like sine x, don't they? Okay, they're just sine. And we know sine is a wave. That's where we get the word wave function. That's where the wave function comes out, okay? From these things here. Now, quantum mechanics says that we can't make any sense, or there's no sort of physical understanding of the wave function itself, but when we square the wave function, then quantum mechanics says that that squared wave function shows you where the particle is in the box. It shows you the most probable position of the particle. So the square of the wave function is proportional to the probability, now we're talking probabilities, of finding the particle at a particular point in space. So what does this say? Here is the square of the lowest energy wave function. So the maximum value for this is halfway along the box, okay? So in other words, in this energy state here, you're most likely to find the particle halfway along the box. But here, you are absolutely not likely to find the particle halfway along the box. It's not allowed to be there. And this is crazy. This is nutso stuff. And here, you've got other points where you're not allowed to find the particle. So in a classical world, that particle can be anywhere in that box. There's no restrictions on where it can be, but you go quantum, and then all of a sudden you place restrictions on where that particle can be in the box. Okay? And so this is what I'm saying here. So here's your lowest energy square of the wave function, and that would be a snapshot of the particle. You take a snapshot of that box at various times, you would get something looking like this, where the particle is bunching up towards the middle. That's the most probable place to find it, okay? And then in the first excited state, if you want to call it that, the particle is most probably going to be there or there and never there. And in the second excited state, again, bunching up there, not allowed to be there, not allowed to be there. You get very, very energetic. And then you find that the particle can basically be anywhere in the box. When you get to very, very high energies, okay? Or very, very large systems, like maybe the macroscopic world that we live in. Which is why we don't see the effects of quantum mechanics on the big scale, because they only become really apparent on the small scale. So here are the weird things. Here are the weird things. So as I've said, in a classical sense, the particle has got an equal probability of being anywhere in that box, but quantum mechanically, nah. Okay? And that's just nuts. Why should there be restriction on where the particle can be? Ask quantum mechanics. Okay? Second thing, okay, there are points where the particle can't be. Okay, it just can't be there, and that we have no conception of. These special points are called nodes in the wave function. This is weird. Energy is not continuous. You go to the microscopic scale and energy isn't continuous. It can't have any energy it wants. It can only have certain definite energies. Bizarre. Totally at odds with our way of thinking, with our macroscopic way of thinking. The lowest energy of the particle, those of you who are paying attention, the lowest energy of the particle isn't 0. Now that's just insane. How can the lowest possible energy not be 0? Well, quantum mechanics says so. So there's a non-zero, zero of energy if you want. This is called the 0 point energy. And if you go search in YouTube, you will find the wackos out there saying that, oh, I can extract the 0 point energy and this is a limitless source of energy for the world. Don't believe them. Okay? And 0 point energy comes back to Heisenberg and the Heisenberg uncertainty principle, which I'm sure you've all heard of. The fact that there is always an uncertainty when you multiply momentum and position. Okay? In other words, you can know the energy of something but you don't know where it is, or you can know where something is but you don't know its energy. That's the Heisenberg uncertainty principle. And again, just totally wacko stuff. And when you get to high energies, then your quantum mechanical system starts behaving like a classical system, and this is normally the stuff that we see, unless we start looking at the very, very small. Okay? Now, in chemistry, we're interested in bonds between atoms, and we can model those bonds as a spring. We call this a simple harmonic oscillator. And a spring behaves in the same way as a pendulum, okay? There's a pendulum like so, okay? And we can do the same thing. We've done this particle in the one-dimensional box. We can also do the Schrödinger wave equation for the simple harmonic oscillator, for a spring or a pendulum. And these are the wave functions that we get for these. And this is the square of the wave function. And straight away, the lowest energy situation here says, right, if you've got a pendulum, where does it spend most of its time? This pendulum swinging, it spends most of its time. Oh my God.
On the side.
Oh my God. Right, at the periphery, at the edge, doesn't it? It swings up, stops there, swings, pop, pop, pop. It spends most of its time at the edge. No, not quantum mechanically, it doesn't. It spends most of its time in the middle. Okay? And frighteningly, conceptually, here we go here, it can spend most of its time there and there, but it can't be there. It can't be in the middle. How in the hell does a pendulum get from there to there without going through the middle? This is quantum mechanics, though. And this leads to this thing called quantum tunneling. Things can go where they shouldn't be allowed to go because they haven't got the correct energy to get there, but even so, they can still get there. And this here, this is quantum tunneling, where it's outside of the potential well it can get out. Okay? Weird, okay? Very, very weird. Right, why am I as a chemist talking about basically physics, let's say? Well, the solution to the Schrödinger wave equation tells us a hell of a lot in chemistry, okay? And we can take the simplest possible chemical system, the hydrogen atom, we can set up the Schrödinger wave equation for this, and after about 10 pages of mathematics, we can solve it. I'm not going to do that, you'll be glad to hear. And when we solve it, we get wave functions that look like this. Now, if there are any chemists in the room, they will immediately say, oh, look, that's an s orbital, and those are p orbitals, and those are d orbitals, and those are f orbitals, okay? And these are exact solutions of the Schrödinger wave equation for the hydrogen atom. And orbitals, conceptually, for chemists, are our bread and butter. We say that these are the places that electrons live in an atom. They live in orbitals, okay? And so that's really, really important for us. And the definition of an orbital is a one-electron wave function. It's a solution, it's an exact solution of the Schrödinger wave equation for the hydrogen atom. And you think, wow, that's great. Yes, it is, except, well, we can solve the Schrödinger wave equation exactly for the hydrogen atom. We can do that, that's fantastic. But any more complicated atom than hydrogen, for example, let's say helium, you know, one nucleus, 2 electrons, can't do it. You cannot solve the Schrödinger wave equation exactly for anything more complicated than the hydrogen atom. And whose fault's that? It's the bloody mathematicians, okay? It's their fault because they have yet to come up with an analytical solution of the three-body problem. You take 3 particles in space, you can't solve that system exactly and know what those positions are going to be at any point in the future. And as long as that's the case, we're never going to be able to solve the Schrödinger wave equation exactly for any atom more complicated than hydrogen. You might think, okay, well, there goes that. But, thankfully, we can make very, very, very good approximations which are based on the solution of the Schrödinger wave equation for the hydrogen atom. In other words, they're based on these orbitals here. And we can get really, really, really good approximations to what's actually going on, okay? Right, so we get to the cats, or a cat, let's say. Funnily enough, the Schrödinger wave equation invented a whole lot of sort of conceptual difficulties, some of which I've just sort of outlined to you there. And so Schrödinger in about 1936 or 37, in answer to Niels Bohr, came up with this thought experiment, a Gedanken experiment as he called it, okay? He said, right, let's put a cat in a closed box, and in that closed box, we're going to have a radioactive source which is going to decay at random, okay? Because radioactive decay is a random process. And when that decays, it is going to cause this hammer to drop. This hammer is going to smash open a vial of poison, and the cat is going to die. Okay. So we put the cat, get him there, in the box with the radioactive source, with the poison, close the box, and then the question is, without opening the box, is the cat alive or dead? And this is Schrödinger's cat. Okay, so is it not? Okay, so that was sort of the paradox that Schrödinger came up with for discussion. So, you know, what is going on there? Is the cat alive? Is the cat dead? Or is the cat both alive and dead? Okay, now there's a question that probably you didn't think about. Now, we have this wave function. So the wave function, like we were talking about before, so this wave function for the box and the cat and, you know, everything inside the box. And now the wave function for that system has to be a combination of both the alive wave function, where the cat's alive, and the dead wave function, where the cat's dead. And we can't know whether the cat is alive or dead until we observe the system, until we open the box. And when we do that, one interpretation of quantum mechanics says, right, the wave function, which is a combination, which until that point is a combination of the alive and the dead wave functions, is forced to choose, so to speak. And in other words, what happens there is that the wave function collapses. We talk about the collapse of the wave function into one and only one of the two possibilities. Either the cat's alive or the cat's dead. Okay? And that's called the Copenhagen interpretation of quantum mechanics. Okay? That's I guess, sort of an idea of that, shall we say, okay? Now, that's not the only interpretation of quantum mechanics that we have. So we have this guy here, gosh, who would have thought he'd been an American in the 50s, huh? I mean, you know, gosh. So his name is Hugh Everett III, and I think this came out of his PhD. He was a rather precocious young chap, and he came up with a thing called the many worlds interpretation. So, get this. So instead of collapsing the wave function, okay, when you open the box, the wave function either turns into the alive wave function or the dead wave function. In the Everett interpretation, the many worlds interpretation, he says, right, when I open the box, we have both things happening. So the cat is alive in one universe and it's dead in another universe. Okay? And so therefore, every possible action that we have, where there is a possibility of different outcomes, they all occur, but they all occur in separate universes. So somehow, parallel to ours, is another universe in which the cat is now dead rather than alive. And on and on and on we go. Hence the many worlds interpretation. All you need for that is an infinite number of universes, and then it makes sense. But these universes apparently can't communicate with each other. Okay? And this was Everett. So there's still debate about this. Which is the correct interpretation of quantum mechanics? You know, it's heavy stuff. Heavy stuff. Anyway, Hugh Everett III had a child by the name of Mark Everett. This guy here, and he started a band called Eel, not just Eels, sorry, not the Eels, and they're sort of a bit Pink Floydy. They're just anyway, you can listen more later. So what does this all mean? I don't know. I have no idea. That's why I gave the talk, because I don't understand this. If anybody does, please tell me. Okay. Now, this guy, Richard Feynman, a slightly better intellect than me, let's say. Okay, so if you think you understand quantum mechanics, you don't understand quantum mechanics. That stands to reason. Or I think I can safely say that nobody understands quantum mechanics. He won the Nobel Prize in Physics, and he doesn't understand it, so what chance have I got? Okay. So, what's sort of the take-home message? The take-home message, we started with Newton, and Newton had these laws of motion where you could predict the future state of the universe at any time. And then Planck and Bohr and Einstein and Heisenberg and Schrödinger came along and said, nah, that's no longer true. We've got a new physics here. We've got this new physics called quantum mechanics, and quantum mechanics deals in probability, not certainty. And that's a bit scary when you think about it. We're used to getting answers in science, okay? We're used to getting definite answers. But quantum mechanics doesn't give you that luxury. You haven't got scientific certainty anymore. Determinism doesn't exist anymore, not on the quantum scale anyway. And it's all about probability. And Einstein did not like this. And Einstein said in German, God does not play dice, or words to that effect. Okay? God's not a gambler. It's not about probability. He spent the rest of his life trying to sort of mesh relativity and quantum mechanics, and he just never succeeded. Nobody has since his day, okay? So you've got Feynman, you've got Einstein, you've got the finest minds in the world trying to sort this out, but they don't know what the hell's going on then. What chance us? So I finish with this here. Quantum mechanics is currently the best theory that we have for describing the universe. There may be a better one out there, but at the moment we don't know. We may or may not find a better way of describing the universe. It might be like Newton's laws. They're all good, and then a couple of hundred years they're superseded by something else. We don't know. Is there a better one? Is there not? I don't know. But somebody might find out one day. So, thank you for listening.
Any questions?
Brilliant lecture, thank you.
Come.
The missing link, maybe to tie that in, so where you had a little radioactive sign in the box. So we skipped over this a bit quickly for me. So can you bring, because I usually when I go through it in my mind, I bring in the double slit experiment.
Yeah.
So that I was hoping to have reiterated by you a little bit, like when you start observing it, things start to behave differently.